All right, let's get started with section 5.4, and our learning target is going to be to solve linear quadratic systems. And honestly, I think this is a pretty good lesson to have right before the final exam because it's going to require us to remember a number of things from what we've done this first semester. Our first two questions are warm-up questions, which ask us to graph. In letter A, we're graphing an absolute value function, and in letter B, we're graphing a linear function. I recommend you pause the lecture and try it on your own, and then you can kind of pick up where I start off. Okay, so let's look at our first function here. What I notice right away is I have an absolute value bar, so therefore I'm going to have an absolute value shape, right? It's going to have a V shape to it. So I think about all the things that I know about absolute value. Well, does it open up or open down? Since it starts with a positive, it's going to open up. My slope is going to be that number out in front, so I'm going to have a positive negative 1/2. And then my vertex is going to be at the opposite of the x coordinate, 1, and then just the y coordinate. So my vertex is going to be at 1, -4. And then my slope from here, I go up 1 to the right 2, and then also up 1 to the left 2. And if you wanted to use your calculator to double check any of this, what you can do is use the math button, and then under the num category for number, you should see the absolute value selection. So if you did want to put this into your graphing calculator and look at a table of points, you can do that as well. All right, looking at letter B, thankfully I have an equation of a line and it's already in our mx plus b form, our slope-intercept form, which we really like. So this tells me that my y-intercept is at 1, and then my slope is -3. So I would go down 3 to the right 1. And then I'm going to reverse it on the other side so I can try to draw as many points as possible so that hopefully my line will be pretty straight. All right, great. That was a pretty good warm-up getting us ready for what our learning target is, which is to be able to solve a quadratic linear system both graphically and algebraically. So as we go through this, right, we're going to have a linear function and a quadratic function. So we have a line as one of the things we're graphing, and then another one is our quadratic. And so we're going to try to see where these two things meet. And our possible solutions will either be one coordinate point, two coordinate points, or they will never meet at all. So those are the kind of solutions that we're going to be looking for. So let's look at our first example. We're going to graph each equation by hand, and then we're going to identify the point or points where they intersect. Pay attention to what form is given, and this means for both lines and quadratics. So I'm going to try, right, to use everything that I know about linear equations and quadratic equations to be able to graph this as quickly as I possibly can. So looking at letter A, I immediately see that the first equation is my linear equation, right? There's no x squared in there. I want to convert it into y equals mx plus b form. So I'm going to subtract 3x from both sides of my equation. So I get y is equal to -3x. So right now it's in mx plus b form. The b that I don't really need to fill in as a placeholder is just 0. So that tells me my y-intercept is at 0 and my slope is at -3. Now because I have no idea where my quadratic's going to be, I'm going to take the time to graph as many possible points as I can on this graph. All right, so we've got our linear equation. Try to draw that as straight as possible. Maybe I could do a little bit better there. There we go. Now, let's go ahead and look at our second function, which is the quadratic, right? I see an x squared in there, and this is currently in standard form. So when we graph quadratics that are in standard form, we look for things like, I know right away that my y-intercept is going to be at 0, 6. So that's a point I can put on there. I know it's going to open down because it starts off with a negative out front. And then in order to figure out my vertex, right, I'm going to be doing negative b divided by 2a. So when I do that, my b value is just a 0. So it really doesn't matter what's in my denominator because 0 divided by anything is just 0. So that tells me not only is this my y-intercept, well, it's also my vertex. So I need to grab a couple of additional points to make sure that we can graph this. I know by the negative 3 out front, it's going to be quite a narrow quadratic function, but let's plug in some additional values. If I plug in x is equal to 1, I'll get 1 squared, so I get 1 squared, which is 1, times negative 3, which is negative 3, plus 6, I get y is equal to 3. So the point 1 is on my quadratic. I then reflect that over my axis of symmetry, right? My axis of symmetry goes right through my vertex, so it's going to be really just the y-axis or the line x equals 0. Make sure I'm on blue there. So that tells me, oh, looks like I've already found one of the intersection points, but I bet there's going to be another intersection point down here. So let's see if we can find out where it is. Let's plug in another value. I'll plug in x equals 2. So I get negative 3 times 2 squared plus 6. So I get 4 times negative 3, which is negative 12, plus 6, which is negative 6. So I know the point 2. Oh, there it is. There's another point. It's also on the graph, and then I will reflect that over to the other side. Now I have a nice quadratic function. Oh, let's see if I can erase that. That was not well drawn. It's always hard to draw on this little teeny tiny drawing tablet. Up, bend over, and down. Perfect. Now I can quickly see, right, just by the graph here, I know what my solutions are. So when we write down our solutions, we want to make sure we write the full coordinate point. So my first coordinate point is right here. It's at negative 1, positive 3. My other solution point is down here. It's at 2, negative 6. And those are the two solutions. I recommend you pause the video right now and try the next example, letter B, on your own. All right, let's take a look at it though. The first thing I have here is a quadratic and it's in vertex form. So vertex form tells me it's going to open up. It's a positive out front. My vertex is going to be at the point 3, negative 1. So let's go ahead and plot that. And I know it opens up, and it's going to be a little bit wider than what we normally work with. So now I need to come up with a couple of other points that exist on this function. Well, let's see. Let's plug in a couple of points. Now, I look at this, and I know I'm going to be multiplying by a 1/2 after I perform this operation in here. So before I square it, I really want to make sure that I have an even number that I get out of this parentheses. And what I mean by that, if I were to plug a 4 in here, or an even number to start with, if I do 4 minus 3, I get 1. Well, 1 squared is just 1, and then 1 times a half is a half. So I would be working with half numbers, and since I'm graphing, I do not want to work with half numbers. So I want whatever value comes out of this parenthesis to be even, which means the x value that I want to start with should be odd. So let's plug in a couple of points, and then we'll reflect it. We know our vertex is right here, so that tells me that's also where my axis of symmetry is on this line here. So I'm going to plug in x is equal to 5. So when I do that, I get y is equal to 1/2, 5 minus 3 squared minus 1. 5 minus 3 is 2. 2 squared is 4. 4 times a half is 2, and 2 minus 1 is 1. So I get that the point 5, 1 is on my graph. So I've got 4, 5, 1. And then I'm going to reflect that over to the other side. Now let's do one more, because I think I see the shape, but you never know where that line is going to end up. So again, I want to make sure the number that comes out of here is even, so I'm going to plug in x equals 7. Notice I keep going with the positive numbers, right? They're going to be a little bit easier to work with. So I have 7 minus 3 there, squared minus 1. So 7 minus 3 is 4. 4 squared is 16. 16 times a half is 8. 8 minus 1 is 7. So I get that the point 7 is on my coordinate plane, or is on my quadratic. Go, and then I'll reflect that over. Let's see. Right, we've got 1, 2, 3. Perfect. Go ahead, draw my quadratic. Bada bing, bada boom. Now let's go ahead and look at our next equation. I have x minus y equals 6. I would love to put this in y equals mx plus b form. So I'm going to add y to both sides, and I'm going to subtract 6 from both sides. So I get x minus 6 equals y. Perfect. Now it's in slope-intercept form. My y-intercept is negative 6. Perfect. And my slope is up 1 to the right 1. So I'm going to draw a line. Oh, are we going to hit it? Are we going to hit it? I don't think we're going to hit it. Yep, connect the dots, and lo and behold, what do I see? I see that I am never going to touch the quadratic with this linear function that just has a slope of 1. So that tells me that the intersection of these two functions is no intersection. So my final solution is that there is no solution. These two will not touch each other at all. All right, let's move on to our next type of process. So other than graphing these to find a solution, you can also do this algebraically, and we're going to use substitution, right? This brings us back to Unit 1, the second half of Unit 1, where we were solving linear systems of equations. Now our system of equation is a quadratic and a linear. So here's how you do it. You're going to solve for one of the variables in either equation. I highly recommend, right, kind of just taking, right now I already see this right here is equal to y. So I'm going to substitute that into my very first equation. So I get negative 3x squared plus 6 plus 3x equals 0. Now I just need to start solving, right? So here's how we solve. Let's see if we can kind of remember this. The first thing I want to do is I want to order these, right? I want to make sure that I have my x squared, then my x's, then my numbers. Then I look to see if I have a GCF. Looking at this tells me in order to be able to solve this, because it has 3 terms, I will either need to solve by factoring or by the quadratic formula. I know we don't love the quadratic formula, so let's see if we can figure out how to do it just by factoring. Well, I see a 3 is common to all of these, and I like a positive x squared, so I'm going to factor out a negative 3 from each one of my terms. That means the second sign is going to change to a negative, and my last sign will also change to a negative. There we go. Now I'm looking for 2 numbers that multiply to give me a negative 2, add to give me a negative 1. So I have x minus 2, x plus 1. Hopefully this is starting to come back to you as you look at this. I set each one of my factors equal to 0 and solve. So my first solution is at x equals 2. And my next solution is that x equals negative 1. Now the problem is the solutions to a system have to be a coordinate point. So I need to actually find the coordinate point, the y value that goes with these 2 points. So I'm going to go back to my original equation. I'm going to take an easy one, right? Let's look at the very first linear equation here. So I have y plus 3 times 2 equals 0. That tells me y equals negative 6. So that's part of this solution right here. My next one, I have y plus 3 times negative 1 equals 0. Y equals 3. And to just kind of write it in the correct way, we would write out that our solutions are the coordinate points 2, negative 6, and negative 1, 3, right? If you haven't noticed yet, this was the exact same example that we did over here. Exact same example. I didn't want to say it ahead of time because I kind of wanted us to just work through it algebraically, but so basically I'm showing you two different flavors on how you can solve these systems of equations. Let's look at our next example. Yes, it has a vertex form and then it also has a linear equation, but it is not the exact same example that we did graphically. It is a slightly different one. So what we're going to do here is, right, wherever I see a y in my first equation, I'm going to plug in this whole mess here. Now the problem is, this is pretty messy, right? There's a lot going on. I need to FOIL this x plus 5 squared. Now remember, the quantity x plus 5 squared is equal to x plus 5 times x plus 5. So I'm going to combine everything together here before I plug it into my very first equation. So let's go ahead and do that. So I have 2 times all of this. So when I FOIL this through and I combine my like terms, I get x squared plus 10x plus 25, and then minus 4. I then distribute this 2 through, so I get 2x squared plus 20x plus 50 minus 4. I then combine those two terms at the end. There we go. So now I'm going to take this value and plug it in wherever I see a y in my first equation. So I wind up with 3x minus, of course, a minus, we're subtracting all this, equals 7. I'm going to distribute that negative through. Then I'm going to subtract 7 from both sides, and I'm going to combine all of my like terms. So I wind up with negative 2x squared minus, I've got 3x minus 20x, so minus 17x. And then I have this, negative 46 minus 7, negative 53 equals 0. So the reason why I wanted to do this, right, is I'm trying to figure out if I can factor this. I'm not sure if I can, so I'm going to think about it. Maybe the first thing I want to do would be maybe to factor out the negative 1. Let's see what we get, right? It's nicer working with positive values, right? 2x and 53. Now, unfortunately, this does not factor, so I'm going to have to use our good old quadratic formula. Sorry to do that to you, but honestly, it's good review before the final. I can keep with just this one that I factored out the negative 1, or I can use all the negative ones up here. I just know it will be easier to work with if I don't have that negative. So I have A is equal to 2, B is equal to 17, C is equal to 53. So let's plug that in and we'll sing along. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. There we go. So we go ahead and we figure all of this out. Let me pick up my calculator here. I got a negative value. So this tells me that my solution, so if I factor out the I, let's see, is there any perfect square that divides into 135? Let's see. Nope. Nope, does not look like it. So this is the most simplified version. So you'll notice if we were to graph these, we would get no solution. Now, when we solved it algebraically, though, we were able to find the imaginary solutions. So here's the thing, right? On a test, if I ask you to find all of the solutions, positive, negative, imaginary, real, you'll need to solve it algebraically. If I ask you to solve graphically and the two do not meet, you are allowed to say that there are no real solutions. So that's the advantage of solving algebraically, is I can get the imaginary solutions, whereas when I do it graphically, I can only find the real solutions, because the only thing that we plot on our coordinate plane, at least for now, maybe until you take higher level math, we only plot the real numbers on our coordinate plane. All right, let's move on. Last but not least, we do have a word problem in here. The owners of a circus are planning a new act. They want to have a trapeze artist catch another acrobat mid-air as the second performer comes into the main tent on a zip line. How fun. If the path of the trapeze can be modeled by a parabola, so that makes sense. The parabola, right, that kind of shape is modeling the trapeze artist. And then the path of a zip line is modeled by a linear equation. So I want to figure out at what point can the trapeze artist grab the second acrobat. Solve algebraically and check your solution. So let's go ahead and do that. So I have these two functions. Notice they are both y equals. So I can just set them equal to each other. When I do that, right, I want to move everything over to one side. I want to set this equal to 0. So I'm going to subtract here and move it over to the other side. So I get negative 1/4 x squared plus 2x, and then I have 12 minus 16 minus 4. Now here's the thing, right? I definitely like working with things that do not have a fractional x squared. So in order to get rid of this fraction and to make it positive, I am going to multiply everything by negative 4. And obviously 0 times negative 4 is still 0, so I'm good there. So I get x squared minus 8x plus 16. Now I'm going to see if this factors, right? It would be great if it factored, and lo and behold, it does. X minus 4 times x minus 4. So that tells me at x equals 4 is the point that we should let go of the zip line. So I'm assuming that x is going to be our time and y would be the height. So that tells me at 4 seconds, he should let go of his zip line and jump into the trapeze artist's hands. And if we wanted to figure out what the height would be, I could plug this into my equation. And I'm going to pick the easier equation, right? So I get 8 plus 12 equals a height of 20, whatever the units are, because I do not see it listed on this particular question. So when in doubt, even if it's a word problem, if it's asking you to find their intersection point, just go ahead and solve it as you normally would. All right, thank you. This concludes this unit 5 for Algebra 2.